Make sure you try this out first. Pause the video if you have not. This first one is about a graph. Remember I mentioned stretching, right? So when a thin metal wire is stretched, reminds me of chapter 9, it becomes longer and thinner. That says it's a change in L and also a change in area or diameter lah. And then because of that, the resistance of the wire changes. Yes, we looked at that animation just now. But here's a very important tip. This is not always true for all wires. You might want to look very carefully at each question that talks about stretching. So here, the volume of the wire remains constant. Okay, so which graph is extension with resistance? So X and resistance. So if you find it hard to imagine, just draw lor. You have a wire, then you pull it already, it becomes longer but kind of thinner also. That's basically what I'm saying. And they say, how does the resistance change when you pull it out? Actually, for simplicity's sake, I'm going to make this also start from the tip. You'll see why later. So what is changing here? How we have resistance, right? Rho L over A. And hopefully you got the chance to play around with this thing. We want the relationship between R and X. So R and L, you might say, oh miss, we just do R and L. Should be a straight line graph increasing, but there's no answer. Why? Because, hang on a second. R is changing, L is changing, A is also changing. Getting longer, but then area decreasing. At different factors, they are not linear. Well, this one is linear. This one is not linear. Anyway, the problem is we have too many things changing. So we cannot just say a relationship of R with L, R with A, because both are changing. So what we could do though is substitute out some values. What do I mean by that? A is changing, and this key, volume is constant. Volume is actually the cross-section area times the length. Pi r square h. Pi r square is the area, h is the length. So V equals to AL. So if I plug my A here, I get V over L. Now the purpose is to get everything only in terms of L and everything else constant. Okay, so rearrange already, then what? This will be rho L square over V. So then, now you see, rho is constant. Volume is constant, good. L is the one that's changing. So it's getting longer and longer. But look at this, we have a power. So now we can say for sure, all right, R is increasing also at a quadratic factor because of the square there, L squared. So you summarize as R something 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 proportional to L squared. Now let's look at all the other stuff. So L squared quadratic graph means not this shape and not this shape. So we're stuck with A and D, but how do you know which one to choose? The difference is the intercept. Why does the intercept matter? Because you see, originally you have some L0 original length. Then you extend some more, that's your extension. So that's all what you call change in L. So that means when your extension is 0, this is where 0 extension is, you already have some length and you already have some resistance, R. Okay, I repeat. Here, this dotted line is where extension is 0. Means your wire is not stretched. See, it's still fat and nice. But there's already some resistance there. So you see, this one, cannot be leh. It says when you didn't extend means 0 resistance. 0 resistance? No such thing. Okay, so this one is out. That leaves us with A, which is quadratic shape, yes. But also, when the extension is 0, you already have some initial resistance before you stretch it. That's more like it.